Yes, would you please share your slides?
Are they visible?
Yes, they are visible. Yes. All right. So as I said, our next speaker is Ayan Mukhopadhyay from IIT Chennai, and he's going to tell us about quantum thermodynamics, erasure, entanglement, and holography. Yes.
Okay, thank you for this introduction, and I'm very, very happy and very grateful to get this opportunity to give this talk in this in the international version of this Indian string meeting. So my talk will be already, the title has been announced and it is here. So what I will do, I will first start by explaining these two words, quantum thermodynamics and erasure, which may not be so familiar to all. And before going there, this talk is based on this paper that we recently had. It's a very recently started program. Although we started working on it a little bit earlier, but we started understanding better what we are doing only recently, and we have this paper out now on the archive, and there's one coming very soon, hopefully this month itself. And there are actually many upcoming works which are coming on. I mean, we have already results which are going to be published with many other collaborators also. And I'm very thankful to have a very good postdoc, Pratik, and very good student, Tanay, who has done much of this work for this project. So, okay, so let me give some idea about what I'm going to talk about, this field of quantum thermodynamics. So to introduce these ideas, let us take some two simple questions that one can ask for a finite dimensional quantum system. The first question is, what is the minimum cost of preparation of a given mixed state? I give you a mixed state, and how much minimum cost, what cost in a single shot, means in a single operation, that you have a single operation to prepare the state, and what's the minimum work that you require to do it. And also you can ask a similar kind of question, what's the minimum work that can be extracted from the state? For example, you can make the state go to another state and in this process extract work. So how much is the maximal thing that you can do? And of course, here this assumes certain Hamiltonian and certain thing. So so basically the answer to this process, answer to both questions were given by Junger Halpern and Joseph Rennes in 2016 in a remarkable paper. And what they were able to show that for a single shot process, in one shot process, the answer to both questions are in a quantity called hypothesis testing relative entropy. You might know relative entropy, but hypothesis testing relative entropy is a certain version of that, where you have only one copy of the state and not several copies. And this relative entropy is between the state that we are talking about and a suitable Gibbs ensemble, a thermal state, is determined by the energy. This hypothesis, and of course, there's an epsilon approximation, because you can only prepare a state within an epsilon approximation. So this epsilon approximation included in this definition of hypothesis testing relative entropy. So these gives the bound. So this is a very simple. This comes from quantum information theory. More generally, you can ask the question, how much resource a quantum channel needs, because resource is not only energy, but also other things. For example, entanglement. For example, if you have to work a teleportational quantum channel, it requires non-local entanglement. So the question is how much non-local entanglement you need, or if you need energy, what is the energy cost for operating the channel? And similarly, you can ask what is the maximum rate of a catalytic reaction. You can ask what is the maximum energy efficiency of a quantum engine. Now, this is also different for a quantum case, because, for example, if you have just isolated hot and cold system in contact with each other, heat can flow only from the hot to cold. But in quantum, if you allow entanglement, initial entanglement between the hot and cold bodies, and they're isolated from rest of the universe, heat can still flow in the other way without violating second law, because entanglement entropy takes care of it. So you see that you need many other resources, not only energy, but also entanglement. And you can ask, what are these kind of resources needed to operate a quantum engine? How much of heat supply, how much of entanglement supply you need? And similarly, if an irreversible logical operation, this is a sort of Landau erasure constraint. If you have irreversible logical operation in a quantum computer, is there also an irreversible thermodynamic cost? And so these are the very general set of questions. It was very nice review by 𝗬𝗪𝗏 and Gaur in 2019 review of modern physics volume. You could look up there, and then most of these questions are known in the context of finite dimensional systems. So not much about many body systems. So here holography is promising, because firstly, you might think that in large N limit, the answer to these questions might be simple for whatever reasons, because large N things do simplify to some extent. But there is also opportunity in holography, because there are these prescriptions to compute entanglement entropy. There are now even prescriptions to compute entanglement negativity. And also we know that modular Hamiltonian or slightly excited states, slightly excited from vacuum, are related to canonical energy, at least if you take ball-shaped region. So you can also compute relative entropy. So there are some things that we know how to compute in holography. And holography also provides an independent additional motivation, which is as follows, that quantum engines can be also made out of evaporating black holes. So you could form a black hole, make it evaporate by changing boundary conditions. You can make it either completely transparent, or you could make it absorbing, or reflecting, sorry. So you could do all of that. And so I will, at the end of the talk, I might have a few more things to say. There's an intimate connection now between quantum thermodynamics and quantum information aspects of gravity, with profound implication for the information paradoxes. So that gives you an additional motivation to also do these questions. So what we will do, we will try to look at one such set of questions in this talk and what we have been able to answer and the method. So what is the simplest question that you can ask in this context? So for good reasons, we would take a 2D holographic system and not, it is much easier to answer this question, because as we will see, easier to compute entanglement and the other stuff that we need. So you connect it to an infinite energy memoryless bath. It's a typical simplest setup. It's a bath that has infinite energy and has no memory. And you start with a quantum equilibrium state. This is analogous to the generalized Gibbs ensemble. Essentially, these are like 𝗲 hair on top of a thermal state or a vacuum. And then what we do is we let energy and momentum flow from the bath to the CFT. So what happens is that your one quantum equilibrium state goes to another quantum equilibrium state. So what we ask is the following question. So suppose a given quench protocol, suppose we think of a quench protocol that drives such a transition. You start with one quantum equilibrium state, we go to another. Is this physically possible? So is there a physical process that can be applied by changing the couplings of the theory or driving some quench such that you can go from state A to state B? And this is a question that's already relevant for cold atomic gases trapped in a laser. So you could think in a laser, laser can be thought of as an infinite dimensional. It's a 3D thing and a 2D thing, lattice on top of it. So it's like a laser is practically would be an infinite dimensional bath, if not, and in some approximation, it is memoryless, say, and then you could ask that I change properties of the laser that change properties of the couplings between the atoms, and I can drive a quench, and therefore I can inject energy and momentum that allows this transition from state A to state B possible. Now, classical thermodynamics will simply tell us that for an infinite bath, that your entropy and temperature must always increase in the system. And this is also obvious in classical gravity. If you have a classical gravity with Dirichlet boundary conditions, nothing dynamical in the boundary, or even then the entropy will always increase. And so this is the entropy has to increase monotonically, even for other boundary conditions. And quantum thermodynamics will tell us that that indeed, I mean, that in all known, even as in finite dimensional cases, it will not violate classical thermodynamics, but it will tell you that often what we think in classical thermodynamics is sufficient is insufficient. You need more constraints. So for one of the surprising results we will see that if you increase the temperature by such an amount, then there is both a lower bound and an upper bound to how much the entropy can increase, which is surprising because classical thermodynamics will simply tell you both will increase, but the lower bound is surprising and upper bound is also surprising, equally surprising. So these are the things that we will see soon. This is simply examples of it. But these kind of questions also incorporate erasure, because when you go from one state to another, you could think of going from a inhomogeneous state to a homogeneous thermal state. So that would be like erasing information. So it's already so all of these things are included in this very general class of question. So all this is a simple question, but it already involves many non-trivial protocols. And the simplest tool that we can use to analyze whether such a process is possible or not possible is a quantum null energy condition. I don't have too much time to elaborate, but originally it was proposed by 𝗏𝗏𝗃-𝗏𝗃 in 2016, based on the quantum version of the Rai-Choudhury equation. So there naturally this generalized entropy came up, and then you can take the limit where gravity is switched off, and then you get a condition with pure quantum field theory without gravity. And this condition turns out to be that the expectation value of the energy momentum tensor is essentially greater than the second derivative of the entanglement entropy. Now in 2D CFTs, this precise statement was first made here, where this inequality can actually become an equality also. And then it was proved rigorously in 2D CFTs generally by Srivatsan, Faulkner, Khankar, Wang. And of course, there are many, many other works where this has been proved in different other contexts. And so there's a double, you can get a list in a paper. So essentially what is the statement is that you take a interval where you are, and this is your point of observation where you are measuring these non-vanishing components of the energy momentum tensor, which are t++ or t-. And then you take any interval that ends at this point and you deform the endpoint in dx plus or dx minus direction. And you compute the variation of the entanglement entropy and you do this deformation. So that defines the right-hand side, these two terms. And this has to be, this minus this has to be greater than or equal to 0. And any state or any theory, any geometry in the bulk which will violate this condition cannot be physical, it can relate to a physical state. Okay, so this is now we come to the setup. So we have to investigate these classes of questions. We have to consider some very general geometries that does such transitions between quantum equilibrium states. And this is the most general answers that you can take. So M is a function of T and X, J is a function of T and X. And now we want these to satisfy Einstein's equations, which are of this form. Now here is something that we will do is that what we want to go from one quantum equilibrium state to another quantum equilibrium state. And these will be essentially general, each one will be a Barradas geometry on its own. So this is what is well known. And that actually tells you what kind of TMN you can take at all, if any kind of TMN. And so we will be completely agnostic about what is the content of the TMN, right? So we don't know what bulk matter it is made of, because so we can do a very general analysis. We don't care about it. But of course, this TMN has to be conserved in this metric, whatever TMN we will take, and will provide the right Israel junction conditions that can give you a transition from one Barradas geometry, any arbitrary Barradas geometry, to any other and arbitrary Barradas geometry. So if you allow such, the most general such class of states, TMN would be of this form, which is conserved in this metric without applying anything else. Now, the Einstein's equations will simply reduce to these two equations, constraint equation, rather simple. So actually, you can easily see if I put this P and Q, which determines this energy momentum tensor completely, to 0, the most general solution are of this chiral form. And these are essentially the Barradas geometries, where this M and J takes these chiral forms. And the one good reason to call them quantum equilibrium states is that these inequalities are completely saturated in this equals to 0. And this was actually first shown by Daniel Grumino and Christian and Shaheen in a paper, Sheikh Zabari. So I'm sorry I didn't put this reference in this year. I should have. So these these inequalities are saturated in all of these quantum equilibrium states. And these are essentially Virasoro-Hare on vacuum or thermal states, but some of them are much more exotic because you have to use this co-adjoint orbits or Virasoro group. So I don't have time to explain the whole class of such states, but for the moment, this is good enough for us. Now, if you have to drive some instantaneous quenches between two things, you have to simply M of this form. So for t less than 0, you have one quantum equilibrium state, while L plus and L minus are given by this I's. And for t greater than 0, you have two other class of quantum equilibrium states, where this L plus L minus given by this F's. So you have 4 functions, one for t less than 0, and one each for the chiral component, not for the anti-chiral component. And yeah, so you have 4 such functions. And then P and Q are then delta function-like. So basically, it's a null shell that is following in, but it's an inhomogeneous null shell, where P and Q are given by this solving these equations is rather trivial. It will be simply given by delta functions and the differences of this L plus and L minus. And if you do holographic renormalization here, the boundary state is the boundary T plus minus that. So this is the thing that appears here, which is of interest. So that would be simply one quantum equilibrium state before T less than 0, and another quantum equilibrium state for T greater than 0. So that's rather simple. So that is exactly what you see with a factor of C by 12 pi, which is well known. And these states satisfy these word identities where del mu T mu is equal to this, where F nu is simply is Q and P, these delta functions. So basically, this is Q is the heat injection and P is the momentum injection, both of which are inhomogeneous, in order that this can happen, this transition can happen. So this is basically the simple gravitational description of such states, where you are completely, you don't ignore, you can completely be ambivalent about what makes up the bulk resistance. But anyway, when the quantum null energy condition is satisfied, we also find that this bulk matter satisfies classical null energy conditions. So this is sort of usual classical bulk matter you need. You do not need exotic ones to make it happen. Okay, so now we have found out this method, cut and glue, in order to analyze such things. So this method tells you how to compute the entanglement entropy and how to compute its time derivative. And it goes like this. So what you do is that you know that before T less than 0, you have a Bernoulli's geometry. After T greater than 0, you have another Bernoulli's geometry. You can do uniformization maps, which we found out first, I think, in the Eddington-Finkelstein coordinates. So these are completely well known. We have completely found it out, not yet exact ones. So that you can use to go to Poincare coordinates, but there are two different Poincare coordinates. Now, when you do that, so your gluing surface is simply T is equal to 0 in the physical coordinates. That gets two images, one here and other here. So you have to go from one image to the another, and that can be simply gone by requiring continuity of the physical coordinates R and X. So if you just simply do that, you can know which point here to identify with which point on this surface. And then the geodesics are trivial because geodesics are simply semicircles. And now we have also a continuous version of this, which can not only handle instantaneous quenches, but also can handle smooth or other time varying things. As long as you keep geometries of this kind, we would be able to handle these kind of analytic methods now. So therefore we can compute many things analytically. So all the results are analytical. Of course, sometimes we do semi-analytic because the expressions are often like extremely long and we cannot simplify, and then you can only plot them. But otherwise, where we can simplify, we have been able to simplify, and our results are all analytic. So let's see what QNEC allows. And the first type of question you could say that let's just look at initial and final geometry of simply BTZ black holes. So you have T plus plus and T minus minus, both to be constant. There's mu plus and mu minus. So mu plus is the right moving temperature, mu minus is the left moving temperature. The Hawking temperature is a geometric mean roughly, and the entropy density is simply the sum of mu plus and mu minus. So this is how we describe the initial and final states. And then you can see what QNEC is allowing. So first of all, the strictest conditions of the quantum null energy condition only comes from very, very large lengths, that is L goes to infinity, as you can see here. So your Q plus and Q minus are those inequalities which have to be greater than 0. So they take the minimal value when L is largest. So as you can see, that is sufficient to look at the semi-infinite interval. And these are again our analytic results that we have plotted. So for a special case, I can actually show you how this thing works. So if you look at Q plus Q minus, and you take mu plus and mu plus and mu minus and initial mu's, and mu plus f and mu, and the final is mu plus f is equal to mu minus f is equal to mu. So it's a non-rotating final state. And we have taken a semi-infinite interval. So for that, Q plus and Q minus behaves like this. So one surprising aspect of this result is that if you start from the vacuum, mu plus I and mu minus I are 0, then you see that the whole thing vanishes for all time. It is surprising because the entanglement doesn't, if you go from vacuum to a finite temperature state, the entanglement doesn't thermalize instantaneously. It takes a lot of time. It takes time of order L by 2 of the interval to thermalize. So exactly L by 2, sorry. So now here, your T min u, of course, thermalizes instantaneously. It is surprising that S double prime plus this thing for a very larger length is like a 1-point function. It also gets saturated to the final value. So that, but of course, if it is not the initial state is not the vacuum, you get a non-trivial dependence, which is actually determined by the final mu. So this is one example. But anyway, so without going into many more such examples, let me just give you some allowed transitions. So suppose if you start from some mu plus and mu minus of this value, 1 and 0.8, you ask what are the other possible final states that do not violate the quantum null energy condition, and this is the answer that we get. So as you see that your mu plus, the final mu plus and final mu minus both have to be greater than the initial one, which essentially implies the temperature and entropy both should increase. However, it is not sufficient. So let us, for example, look into this graph. So suppose we fix a final entropy density, which is simply mu plus plus mu minus, is given by this straight orange line. It's a isentropic surface, isentropic line. Then you see there is this, these blue and orange lines are isothermal lines. So you see that they're bounded, the minimal and maximal values of T are bounded both from above and below, which is surprising because if you just use classical thermodynamics, everything here will be allowed, but quantum null energy condition is still violated. So, so this is the white region where it is not violated. I'll explain the gray region later. Similarly, you could see for this example, if you pick up a final temperature instead of final entropy density, there are bounds on the minimal and upper and lower bounds on the entropy density that is allowed in the final state. So this is a very, very surprising result. So for a given increase in entropy, there are both lower and upper bounds on increase in temperature and vice versa. So the black lines here are simply given by non-violation of QNEC at T is equal to 0. And these gray lines comes from later time evolution that you have to basically look at Q minus. Okay, I don't have much time to go into the details. So, but there are two crucial later results that I want to highlight. So whenever the transition is allowed, the Q plus always increases monotonically and the Q minus always decreases monotonically with time. At an infinite time, we can exactly tell you what are the final Q minus and Q plus, and these are these values. So one interesting thing that you see that if the final state is non-rotating and you start with the vacuum, Q plus is equal to 0, which actually says that Q plus remains 0 for all time, recovering the result that we got earlier. And Q minus, so this is Q minus will always decrease and Q plus will always increase. So this is the result that we get. And actually we don't, so a more general result what we study is that if there is no energy momentum excitation that leaves the interval, then QNEC inequality always behaves monotonically. And we do not really know why, because there's no good explanation for this behavior. So we would try to understand this better. Okay, so now let me come to another such example, which is Landauer erasure. So in Landauer erasure, what you do is that the basic Landauer principle tells you that if you want to delete information, it requires irreversible energy transfer for information carrying degrees of freedom to other degrees of freedom. So this is actually a statement that was made by Landauer in the context of classical statistical mechanics, but later Reeb and Wolf made a very concrete statement in the case of quantum statistical. The most important thing is there should be any irreversible logical operation must also involve irreversible thermodynamics, which is irreversible energy transfer or entropy increase. So one of the Landauer erasure protocol that we can study is that you basically start from a inhomogeneous Van-Adolph's geometry and then you go to a homogeneous one. So you see in 3D CFTs you cannot homogenize. It will not thermalize on its own because tidal excitations are live forever in pure gravity. So you need to do something. So you have to quench to do it. So this is a quench that you do. It's the same kind of geometries, of course, that we discussed earlier. It's simply that you are not taking a homogeneous state to begin with. And your L plus minus takes this form where Ws is roughly the deformation, is a diffeomorphism that allows you to do it. And this diffeomorphism, we take it to be Lorentzian. But L plus minus take this form, as you see that the classical null energy condition is violated here. But the state is allowed, no problem, because a quantum null energy condition is satisfied long before the quench. So there's nothing wrong with it. So yeah, so now you want to see how much of information that you are deleting here. So for that, you look at this class of excitations and you compute the entanglement for a large entangling length, and you see that the first answer comes out to be thermal, and the thermal has exactly this temperature T by pi. And then there's a finite piece, and then there is a terms that are suppressed by L inverse. So essentially, you can identify this as the amount of information that is there in the system that is non-thermal, that carries information. And B is the length scale that where information is localized. That you can see either from this Lorentzian form or from the form of L. You could say that you could easily see that B is the length scale where the information is localized. So now, okay, so now if you look into it, like what is the minimal energy that, so
I mean, maybe you can wrap up in 5 minutes, including
yes,
questions.
5 minutes, certainly I can wrap up. Okay, so so what you do here is to look into the minimum amount of temperature increase that you need in order to not violate QNEC and erase the information. So if you start with small localized, from large lengths where the information is localized, this final temperature increase actually grows monotonically with the amount of information. And actually you could show a very universal result that if the amount of information is large, or in general, if the minimum amount of delta T will be the maximum value of this Wx, if Wx is very large, is where this Wx is this quantity generally. So basically it means that essentially minimum delta T would be essentially 6𝗋𝐶 of information at very large values of S info. That's what it means. But however, if you keep the localization, if you keep decreasing the localization length, you see that there is a funny behavior. There's a non-monotonic behavior of the amount of a minimum amount of temperature increase that you need in order to delete the information and not violate quantum null energy condition. And actually, this leads to a very surprising result. If you keep decreasing it further and study the thing, what you get is, I'll tell you how it later connects with that figure, is that there exists a minimal length, LC, for each S info such that if B is much, much later than LC, the information cannot be deleted suddenly without creating an infinite temperature state. So if you look into the, so basically, for this amount of S info, if you localize information beyond this length scale, you cannot delete it suddenly. Now, you see what will happen as S info becomes very, very large or very small, this localization length both go to 0. That's easy to see why it should happen in both ends. So when you have no information, basically, then basically you are going from one finite temperature to another finite temperature state. So delta T can go to 0 without violating anything. And similarly, you can argue for this large result, which is actually comes from this result, that there should not be any such minimum localization length. Okay, so but in
Sorry,
you got muted.
Yeah, the speaker was muted. Yes.
You got muted.
yes, I cannot.
You're fine now. I don't know what happened. Sorry.
Yeah. Okay, I got muted. I don't know where I got muted. So I guess let me run through this again. So in this figure, if you have large amount of S info, then the minimum delta T essentially scales with 6𝗋𝐶 S info. That's a result. That's a universal result. And here, what I want to say is that if you keep decreasing the localization length where the information is localized, you see the amount of delta T that you need in order to not violate the quantum null energy condition and to erase the information actually starts behaving in a non-monotonic way for smaller and smaller localization lengths. And then one thing that you see is that for any amount of S info, there exists a certain localization length beyond which if you localize information in shorter length scales, you cannot delete it instantaneously without creating a final infinite temperature state. It's protected against very fast deletion. If you localize beyond this length, you cannot do it. And it's also easy to see when S info is less than is equal to 0, then you don't need any, there should not be localization length because you're basically a homogeneous state, finite temperature state, and you can simply go to the other, there's a minimum delta T is equal to 0 should be allowed. But however, if you keep increasing information, there exists this kind of a thing, kind of weird shape. And if you go for very large S info, you can also say that your localization length, there should not be any minimal localization length, basically due to this formula. So you see this non-monotonic behavior. And so what will happen is as follows. Suppose I choose a localization length somewhere here, and I look into this curve, so initially, so this will actually go to infinity at some point, and again come back from infinity at this point. So there will be some particular value, some range of S-info for which you cannot delete the information at all instantaneously. So that will happen. So that explains this non-monotonic behavior, which goes into two such weird things. It goes to infinity here, again it comes back from infinity somewhere here. So so this is how in middle there will be only complex solutions of your whatever analytic equations that we're using. So so this is how it behaves, and then you see the S-info when it becomes C/6 roughly. When this S-info becomes C/6, there is a maximal localization length, and this is sort of shape dependent. So this is a very new, surprising result that I think you wouldn't have guessed just from the Landauer principle only. So I don't have time for bounding growth of, I simply go to the conclusions of my talk now because I don't have time for this. So for comments and outlooks is as follows. So we only talked about transition. So we talked about transitions from between two homogeneous states, and then from one inhomogeneous state to homogeneous state. But we can also ask, what about transitions between inhomogeneous states? So can we amplify an energy perturbation, or is there some kind of group operation that are allowed? So this is the questions that we are trying to look into. The other set of questions that are also equally important is to say now you can actually look into quantum matter in the bulk, and then you have to compute the entanglement entropy using the Engelhardt world extremal surfaces, not the HRT extremal surfaces. And you can ask the same kind of questions like what QNEC allows, what QNEC not allows. But then you are basically asking some very important questions like, suppose you look into Hawking radiation and you are wanting to do some information task with it, how much resources you need for that, or how much of entanglement between the island and the radiation that is needed for that to happen. So these kind of questions are at the heart of resolving like the Hayden-Harlow kind of mechanism of resolving AMPS paradox. And also you could ask much deeper questions like of a similar kind, what's the efficiency of quantum channels that you can create by using such quantum black holes? So these actually goes very deep into the quantum information theory of gravity in general. Then you can also study other protocols like minimal entanglement require. So these are the set of questions that you can usually handle by this quantum. So we have set of collaborators whom we are exploring different aspects of this. And then you can also ask if QNEC is sufficient. You can also get why should QNEC itself work? You can probably get similar bounds from Rene entropies because QNEC uses entanglement entropy, but there could be some similar null. So there are some proposals that null derivatives of Rene entropies can give similar generalized bounds like what QNEC. And similar, so we are also thinking along these directions. And also we don't have a real explanation why there's a monotonicity in QNEC that doesn't come directly from information theory. So we are exploring those aspects too yet. And the next question is that actually motivated by these set of questions is there really some good connection between resource theory and complexity? Because complexity is about building a gate, and complexity literally takes you how you can prepare a state or something. And resource theory basically asks the same question a very different angle. So is there some direct connection between them, which you can explore using holography? So hopefully I convinced you it's an interesting direction to pursue, and thanks for your attention.
Okay, thanks a lot, Ananda, for a very nice, Ananda, for a very nice talk. And so any quick questions? I think we are already a little over time, but because there's a break probably now, so we can have a few quick questions if there are, or any other comments anyone has. Okay. Okay, so maybe I can ask, one very, so at some point you were describing that, let's say if you go from the vacuum to the thermal state, there's some evolution of this entanglement structure, right? So, I mean, how much of this is in actual quantum field theoretic setup, or maybe in some lattice setup? Do you know if there is any understanding of that, when there is a thermalization process going on or settling down into equilibrium, is there any direct understanding of that from a, let's say, a lattice setup or something like that?
Yeah, very good question, actually. So, yes, so of course, entanglement is something that you can manage to somehow compute in a lattice sphere. And I think there's like, there are DMRG protocols that study evolution of systems in real time, where they are able to compute how entanglement grows. I'm not sure it is very easy, whether it's very easy to compute something like the QNEC. So, or any analog of it. There are some proposals of analogs of QNEC in non-relativistic theories too. But I'm not sure if that is easily computable. So to do that, it's a good question to ask whether you can compute such things in this thing in case of, say, a tensor network at least. So that's a good. In tensor network models, sometimes you can even compute analytically many of these things. And so I didn't get time to discuss, but we have really new analytic results for growth of entanglement, where like general cases for general transitions, which were not known before. It agrees with earlier results. And then there are bounds you could set based on QNEC. I didn't get time. It's on the slides. So like the diffusive growth from one initial state to final state, an exact analytic result in terms of the parameters, what is the diffusive constant and stuff like that. So these things are possible also to probably calculate to some extent in some tensor networks. So there could be comparisons that one can do based on it. But QNEC is a very hard thing to, and this is and we are thinking, we are actually trying to think about this question also, like how you compute it in a tensor network.
I see. Interesting. Any other quick question or comments? Okay. If not, thanks a lot, Ayan, for a very nice talk.